Hello, my name is Jay Gupta, and we've put together this video to explain a little bit of the idea behind this crowdfunding project, converting greenhouse gases into gasoline, one molecule at a time. So plants can convert carbon dioxide into the fuels that they need to grow, and we'd like to do this using catalyst materials. And it turns out there's a variety of catalysts that can do this. We've chosen copper oxide because it has unusual selectivity for producing gasoline. So there's a variety of reactions that are involved. Plants use sunlight, and the energy of the sunlight is used to break apart carbon dioxide, which is a particularly stable molecule. So we'd like to use sunlight as well. And this equation represents the energy of the light that's absorbed by a material, by the catalyst, into creating electron and hole pairs, which can drive chemical reactions in the material. So there's a variety of reactions here that we'll be studying as part of this project. I'd like to just highlight that here's carbon dioxide. So that's the molecule that we'd like to convert back into gasoline. And the end product is methanol, which it turns out is a liquid fuel that's already used in combustion engines, like for example, in the Formula One racing series. So if we can understand these series of reactions on this catalyst surface better, we can perhaps improve the efficiency of conversion of CO2 back into gasoline.
Hi everyone, my name is Nancy Santagata. We are going to use scanning tunneling microscopy, or STM for short, to study the reactions that Jay just told you about. So I wrote a lab note that describes how an STM works, but I wanted to show you this is actually the guts of an STM, so it's pretty small. But what we do is we have to put the STM itself inside a big chamber like this. And there's a couple of reasons why we need to do that. The first reason is to keep our samples clean. So we want to make sure that we're only imaging CO2 or water or methanol or the copper oxide catalyst itself. And the chamber helps us do that by allowing us to evacuate all of the air out of it. So that helps us keep the sample clean. And the gases, it's a little bit hard for you guys to see, but the gases would go underneath the table and into the chamber through a precision valve that's located on the back of the chamber. The other thing that's important about a chamber like this is that it helps us control the temperature. And so this tall stack of the chamber is called the cryostat, and that's where we would put the liquid helium to keep the sample cold, to keep all the atoms and molecules still so that we can image them.
Hi, my name is Steven Tjung. So Nancy has just explained to you the vacuum chamber inside this room that encloses the SDM. This room is designed to be soundproof. Basically, it's to reduce vibration from the outside. We're imaging our sample inside there. So the SDM in there is controlled by a computer out here. We start a SDM image scan for you. So right now it's imaging a sample that's currently inside the SDM chamber. And this is something that we're hoping to incorporate in this project for you to be able to control this computer remotely and help us take some data.